So for a general Rn, the only vector operations that are available to you are vector addition and scalar multiplication. You don't have really access to anything else that would take as an input a vector and output a vector. Now, if you already have a bunch of vectors, let's say you have u1, u2, u3, all the way up to um. So you have m vectors in total, and each of them lives in n space. You can produce a new vector by scaling each of the vectors and adding them together, right? So here's an analogy for you. If you've been to Ottawa, you've been downtown Ottawa, potentially u1 would be parallel to Bank Street, and then you're pointing north towards the Ottawa River. And u2 could be parallel to Laurier Avenue, potentially pointing east towards the campus, right? So here's your situation. Well, in theory, then, you could get anywhere in the small downtown core by either traveling in the direction of u1, which is to say going north or south for a little way, and then traveling in direction u2, east or west, parallel to Laurier. But there's a few things you can't do, right? If you're on the streets and you do these things, you know, you might end up going to something like this, for instance. Might end up here. You can't, by just doing these things, find yourself above ground or underground, right? You have to take stairs or potentially your elevator, escalator to sort of leave the surface of downtown. You're stuck on the plane, which is the ground of downtown. That's a linear combination. You can combine together various vectors to obtain a new vector. So if you have m scalars, m being the number of vectors you had to start with, m vectors, the scalars are just real numbers, the vectors are in n space, then you can combine them this way. You can basically take the first vector u1, scale it by k1. Then you take the second vector, u2, scale it by k2, and so on. You do this for all the vectors, and you add them all together. This thing here is also a vector. It is in n space. You can't escape n space, just as you couldn't escape the ground by simply traveling along Bank Street in Laurier. You had to go upstairs or go downstairs before you could actually find yourself in a location other than what's in the ground. Two space in this case. That is a linear combination of u1, u2, and so on. This is a concept that we're going to be using extensively. There'll be a lot of linear combinations, and you have to be familiar with the idea, with the definition. Linear combination of two vectors is just, for instance, some scaling of the first vector, some scaling of the second vector, you add them up. Eventually, we will talk about spanning sets, or spans. And spans, we're not just looking at one linear combination of some vectors, we're looking at all the possible linear combinations. But for now, let's just focus on one. So as an example, let's say you have the vector 1, 2, 3 in R3 and the vector 1, 0, 0 in R3. Both of these are three vectors. You can add them together. It turns out that the vector 17, 4, 6 is a linear combination of these vectors u1 and u2 because you can write 17, 4, 6 as twice the first vector plus 15 times the second vector. Let's see if this is indeed the case. I have 2 times 1, which is 2, 2 times 2, which is 4, 2 times 3, which is 6. And this is equal to 15 times 1, which is 15. 15 times 0, 0. 15 times 0, 0. And sure enough, 2 plus 15, 17. 4 plus 0, 4. 6 plus 0, 6. Okay. So, yeah, 17, 4, 6 is a linear combination of 1, 2, 3 and 1, 0, 0. I'm not telling you how you found it. This is something else we'll talk about and discuss later. But if I give you the scalars, k1 and k2, which are 2 and 15 in this case, and I give you vectors u1 and u2, you can verify that this other vector, this x here, is indeed a linear combination of the vectors. But if you look at 0, 1, 0, which here you see it's written as a row, and here I'm writing it as a column, but I'm really talking about the same things here. If we look at the vector 0, 1, 0, let's see what would happen here. We'd like to write 0, 1, 0 as a linear combination of the other vectors. So the first one was 1, 2, 3. The second one was 1, 0, 0. Well, what do we know? If I write out explicitly the linear combination, what I have is k1 twice k1, 3 times k1, and I'm adding k2, 0 times k2, 3 times k2, and that's just k1 plus k2. This is 2k1, and this is 3k1. Now I can say something about this, right? 3k1 has to be equal to 0, the third component. So that means that k1 is equal to 0. But if k1 is equal to 0, this second component here is also equal to 0. Twice 0 is 0, but it's supposed to be equal to 1, and that's different from 1. So I can't come up with a k1 and a k2 that can scale u1 and u2 respectively so that I get 0, 1, 0. See the difference? Well, here I call them A and B instead, but you see it's the same principle. I'll give you a chance to pause the video and to potentially make sure you understand what's written